Good morning, everybody. On to day two. This is 4.3. The title is Binomial Distribution. Binomial distribution, basically just to use this technique to calculate probability, the following three criteria. So we're going to deem something as success or failure. We'll talk about that in the first example. The trials are identical and the trials are independent. And if you remember back in the day, we talked about independent versus dependent trials. Independent means it's replacement. So if it was a card situation, we would put the card back and draw again and draw again. But you'll see what this means kind of as we go through the formula and the example for today. Okay, so each trial has associated a probability of success. Okay, and we're going to just use a lowercase p for that, and a probability of failure. And the way you figure out probability of failure, since success and failure have to total 1, all probabilities have to equal 1. If the probability of success is 50, the probability of failure is 50, 1 minus 50. Okay, so it's just kind of common sense. Don't worry too much about that formula. Okay, since we're running n trials and x is going to be the number of successes, we're going to use this formula. Okay, so the probability of whatever it is being asked, probability of x, is going to be n choose x. Okay, and we'll see again what that looks like in the first example. And then we're going to take the probability of success to the power of x, the number of times we want these successes. And q will be the probability of failure to the leftover trials. So again, in the actual examples, you'll see better on how this kind of works. Okay, so there's the formula. Once we put it in, it's a lot easier than this actually looks. Okay, so here we have binomial theorem. We did that with Pascal's triangle. Don't worry too much about that. You can use Pascal's triangle and those numbers in Pascal's triangle in the row to solve these, but this is a mathematical formula, easier way of doing it. Okay, so let's take a look at the first example. Olivia just got married and is planning on having 5 children. What is the probability of having 3 daughters? Exactly 3 daughters. Okay, so there is a way to figure this out. We're going to see what that is because there's all possibilities, right? She can have 5 daughters. She could have 4 daughters and a boy. 3 and 2, 2 and 3, blah, 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 and in any order, right? So we're going to figure out what are the exact chances or what's the exact probability of having this exact scenario. Okay, so I just said probability of 3 daughters. So we start with the 5 choose 3. So let's go back to the formula up here. It's n choose x, right? So we are going to have 5. She's going to have 5 kids. She wants 3 daughters. Okay, so 5 choose 3 can be in any order. Order doesn't matter. We're just going with that, right? You're going to multiply that by the probability of success. The probability of success is 1/2. That's the probability of having a girl, having a daughter. And we need 3 of those in our formula. And then the rest, the remaining, is talking about the boys. So there's a 1/2 probability, a probability of failure, let's call that. And we need 2 of those boys. Okay, so the way the formula works, it's 5 choose 3. 5 children choose 3 daughters. Probability of having a daughter is 1/2. I need 3 of them. Probability of having a boy is 1/2. I need 2 of them. When we multiply that out and figure it all out, I did it in steps. Your calculator can do it probably a lot faster. So 5 choose 3 is 10. That's 0.125. That's multiply it all out. We get a 31% chance approximately equal to. Okay, so the chance of having exactly 3 daughters is 31%. According to this binomial distribution, this model. Okay, so that's how it works. Let's do another example. This one involves rolling dice. So the probabilities are a little bit different. So in the successive rolling of dice involving 10 trials, so we're going to roll the dice 10 times. Pick it up, roll again, pick it up, roll again. Find the probability of rolling exactly 3 4s. Okay, so there's so many combinations that can exist. We want to know the probability of somebody that rolls a dice 10 times of getting exactly 3 4s. Okay, so here's how it's going to go. So again, probability of x is whatever it is, whatever's in the question. So 10 rolls, we need to choose 3 of them to be 4s. Okay, so that's how the 10 choose 3 works. The probability of success. So the probability of rolling a 4 on a dice is 1 out of 6. Only 1 out of 6 times you're going to get a 4. All the other 5 times you're going to get different numbers. So 1 out of 6, we need that 3 times. So we take it to the power of 3. We need exactly 3 4s. And the failures is if we don't roll a 4, and that happens 5 out of 6 times, and we need 7 of those in any order. Okay, so 10 choose 3, 10 rolls, 3 of them need to be 4s. The probability of success is 1 out of 6. I take that to the power of 3. I need 3 successes. The probability of failure is 5 over 6. I need 7 of those. When I multiply it all out with those numbers, I get approximately 16%. So there's a 16% chance of you actually getting exactly 3 4s when you roll a dice 10 times. Okay, so that's how binomial distribution works. Let's go to the more difficult problem. And this, if it'll go back to our exclusion. Okay, and exclusion means you take away the ones you don't want. Okay, so the question asks, what's the probability in 10 rolls of it getting at least 2 6s? At least 2 6s. So I get 2 6s, 3 6s, 4 6s, 5 6s, 6, 7, 8, 9, or all 10 6s. Probably not likely to happen, but it could happen. So we want the probability of getting at least 2 6s in this 10 rolls of the dice. So here's how you're going to do a question that looks like this. Your total probability is 1. Any sum of any probability is 1. We're going to subtract the ones that will have no 6s and subtract the ones that get 1 6. So we're going to get the probability of no 6s, the probability of rolling 1 6, and subtract it from the total. So here's that's going to work. And so if you take the total and subtract the ones you don't want, the exclusion, you get the ones with at least 2 6s. Okay, so that's how this one's going to work. Okay, so let's do the probability of getting no 6s, of not rolling a 6. So you have 10 rolls, you're going to choose 0. We don't want any 6s. The probability of getting a 6 is 1 out of 6. We want 0 of those. The probability of getting any other roll other than a 6 is 5 out of 6. That's the failure probability, and we want 10 of those. When you multiply that all out, you get 16%, or 0.16. So there's actually a 16% chance of you not rolling a 6 in 10 rolls. The probability of getting 1 6 is 10 choose 1. 10 rolls, I need 1 of them to be a 6. The probability of success is 1 out of 6. I need 1 of them. The probability of failure is 5 out of 6. I need 9 of them. When you multiply the whole thing together, there's a 32% chance of you rolling exactly 1 6. So when you take the 100% probability minus the 16 minus the 32, you get about a 52% chance of rolling at least 2 6s or better. So it's almost 50-50. And that's how this binomial distribution works, and how you're going to figure out these different probabilities. Okay, so good luck in today's work. There's not too much. On page 167, 1.3, 4C, 7.8, 10A. 10A is just like the distribution, the probability distribution that we did yesterday in 4.1 and 4.2 and 14. Okay, good luck. Many of you have been emailing me and instant messaging me questions. Feel free to do that again. And good luck today. Okay, we'll see you guys tomorrow. Have a good day.